Right, in this video we're going to talk about the binding energy curve. Now in the previous video we talked about what binding energy was and how it's used in conjunction with Einstein's energy equation. Now we're going to look at a binding energy curve, and we need to look at a new kind of variation on binding energy, which is binding energy per nucleon. So binding energy per nucleon is, it's exactly what it is. So if we have a binding energy for a nucleus, as we had last time, and we put that energy in, then what ends up happening is that you could work out what the binding energy was, this total is, per each nucleon that you have there. So quite nicely what you do is you just divide the energy by the number of nucleons that you have to get the binding energy per nucleon. So you divide the binding energy by the number of nucleons. Because this next graph I'm going to show you is not binding energy, it's binding energy per nucleon. And you'll see what I mean when I show you the graph. So this is the binding energy curve. Okay, this is the binding energy curve per nucleon. Now you'll notice that on the side here, it's got binding energy curve per nucleon in mega electron volts. So we're talking about MeV. You will have come across electron volts before. If not, you want to go back, have a look at what an electron volt is. It's very simple. It's just a unit of energy that's very, very small. But obviously we're dealing with mega electron volts here, times 10 to the 6. So still bigger than most, so bigger than a normal electron volt, but still smaller than most units of energy. So when we're looking at this curve, we're going to look at this curve in two kind of steps over the next video or two. We're going to look at it as this side and this side. There's two sides to this graph. This side is otherwise known as the fission side, because this is where fission is going to occur. Don't worry if you don't understand why straight away. We're going to talk about that in a minute. And this side is going to be the fusion side. Now let's just talk about those two words, fission and fusion, real quick. So fission, if you fissure something, you're chopping it in two. So we are breaking up nuclei in a fission reaction. Fusion, when you fuse something, you're fusing it together. So we're joining together nuclei in this circumstance. Now, what always tends to happen, we'll start with the fission side because I think this is the most simple side to kind of get your head around. And then in lesson, we'll go through some examples of this, and then hopefully we'll make a video of an example as well. So say, for example, we have a nucleus that's all the way down here on the fission side of this nucleus. We have a certain amount of binding energy per nucleon. Okay, so it's about 8 in this case, so between 6 and 8. And what tends to happen is what happens when we break up a very large nucleus. So if we have a very large nucleus, let's draw our very large nucleus here. Obviously, I'm not going to draw in all 200 nucleons, but you'll get the idea from the drawing. So there's my very large nucleus, and it's going to break up by a fission. And we are going to get two, it's going to fissure, it's going to split in two. So we're going to get two smaller nuclei. We're going to get two smaller nuclei produced. But in total, we'll generally have approximately the same number of nucleons. Most of the time in fission, you do get quite a few neutrons released off on their own. But in this case, we won't worry about that too much just now, because a neutron on its own does not have a binding energy because it's on its own. It's not bound to anything. So it makes sense that a neutron we can just forget at this moment in time. So what we notice happening is that this molecule, this nucleus here, has broken apart. I'm going to use the right color pen so that you can see. So this nucleus here has broken apart and formed two new nuclei that are much smaller in mass number. Okay, they're much smaller in mass number. So you've got this one here, the blue one, and then you've got the orange one as well. Don't worry, obviously I'm not drawing this counting the amount of dots here specifically, because I'm not drawing 200 odd dots and then 100 dots just for illustration purposes. So what do you notice has happened as a result? Well, yeah, we've decreased the two nucleon numbers. They've got less mass number, so that makes sense that they would be going along there, and because they're on the line, they're on there. What has happened to the binding energy? Well, the binding energy has increased. And you might be thinking, well, what's the point in that? You're increasing the binding energy. Well, remember, what is binding energy? Binding energy is the amount of energy that's required. Now, the way I like to think about this is I like to think about it as being cold and hot. If you need more energy, then it's kind of like getting colder, isn't it? You're having energy sucked out of you. So what you're effectively doing is by increasing the binding energy, you require more energy. So we have an increased binding energy as a result, because obviously bear in mind this is a binding energy per nucleon. The total number of nucleons is approximately the same. So as a result of going up this line, we have increased the overall binding energy. And so by increasing the overall binding energy, we are increasing the amount of energy required to split them into their constituent parts. Well, that's very interesting. And like I said, we've got the idea that having a requirement for more energy is like being colder. So if you've made something colder, that means you've taken energy from it, haven't you? If you've made something colder, you've taken energy from it. And so what happens here is the difference in energy, i.e. the difference in the binding energy that we get here, is going to be equal to the energy that's given off. So the difference in binding energy is equal to the energy that is released as a result of this reaction. So when this reaction takes place, we give off our energy. And so this explains quite nicely how we can get energy from a fission reaction to actually power and make power plants work and generate electricity, because we can take, say, a uranium nucleus, it can fissure. The fissuring process causes an increase in binding energy. That increase in binding energy increases is equal to the amount of energy that is released. Now, we can actually take this even a step further, because as we well know from the previous video, binding energy, or the energy that's released in a reaction of this nature, is also equal to the change in mass times c squared. Remember, E is equal to mc squared. So effectively, the change in binding energy, which is equal to the energy released in this fission reaction, is also going to be equal to the change in mass times by c squared. And these are all of these things linked together. Now be careful, remember I'm talking here about the total binding energy. That's the total, not the binding energy per nucleon. This is a binding energy per nucleon curve. Take your time and just get your head around what's gone on here, because this is not an easy concept to get your head around. Nucleus splits, increased binding energy, it's gotten colder. Please don't think that it's actually getting colder. It's not actually, it's just an analogy. But that idea of getting colder means it's had energy taken from it. That energy taken from it as a result of the change in binding energy is equal to the energy released, which is also equal to a change in mass times by c squared as a result of this fission event. Almost certainly you will have questions about this, and we will talk more about it in lesson. The next video we'll have a look at what happens on the fusion side.